Okay. Welcome to the General Chemistry 1 class. This section is on kinetic molecular theory of gases, focusing on relating gas laws to kinetic molecular theory. In this lesson, we will explain the gas laws in terms of the kinetic molecular theory of gases. Like any laws in science, gas laws are the generalization observed from the variation of the physical quantity of gases as another quantity changes. However, the limitation is that these laws cannot give information about the reasons for the observed behaviors. To better understand the cause of these observations, let laws need to be supported with the models or theory. One model that can be used to explain the behavior of ideal gases or gases that fit the ideal gas law is the kinetic molecular theory or KMT of gases. The KMT describes the characteristics of the particles or the atoms or molecules of an ideal gas. The development of the KMT took more than a century. A comprehensive form of KMT was published in 1857 by Rudolf Clausius, a German mathematical physicist. Different textbooks enumerate the assumption of the theory in different ways, some of which are as follows. 1. A gas is made up of particles, be it atoms or molecules, moving in a non-stop, random, straight line motion. Second, the gas particles are taken as volumeless particles. The volume of particles is too small compared to the volume of the container. Number 3, attractive and repulsive forces among gas molecules are negligible. Number 4, at fixed temperature, kinetic energy is transferred from one molecule to another during the collisions, but the average kinetic energy of the particles is maintained. Fifth, we have the average kinetic energy of the molecules changes and is directly proportional to the temperature in Kelvin. The kinetic molecular theory can also explain the pressure and temperature of gases. Pressure exerted by gases inside a closed container is due to collision of particles with the inner walls of the container. The more forceful and more frequent the collision that the particles make within the inner walls of the container, the greater is the pressure. Absolute temperature. The absolute temperature of Kelvin temperature determines the average kinetic energy of the gas particles. If two gases have the same temperature, these gases have same average kinetic energy. Average kinetic energy is directly proportional to the temperature. Thus, the speed of moving particles increases with temperature. The proportionality of constant is equal to the 3/2 times the gas constant, R. The derivation of the equation relating to average kinetic energy and absolute temperature is discussed in advanced chemistry courses. Let us apply the kinetic molecular theory in explaining the gas laws we learned in our previous lessons. According to Boyle's law, pressure-volume relationship, when a gas is compressed to a small volume, particles collide with the inner walls of the container more frequently, causing the particle to exert greater pressure. Hence, pressure is inversely proportional to volume. Charles' law, the volume-temperature relationship, states that Increasing the temperature increases the kinetic energy of the gas particles, making them more mobile and collide with the container walls more often. In order to maintain the pressure inside, the volume of the container must increase. Hence, volume is directly proportional to the temperature. Charles' law pressure-temperature relationship, increasing the temperature while keeping the volume fixed, causes particles to collide with the container walls more often and with greater force, increasing the pressure of the gas in the container. Hence, pressure is directly proportional to temperature. Avogadro's law, which describes the volume number of moles relationship. Avogadro's law states that, given a container with a given amount of gas, introducing more gas particles at a fixed temperature results in increased pressure due to more frequent collisions with the container walls. In order to maintain the initial pressure exerted by the gas, the pressure must be lowered by increasing the volume of the container. Dalton's law of partial pressure states that, and it perfectly illustrates on the left image, which depicts a container filled with gas A. It exerts a certain pressure inside the container, and on the other hand, the illustration on the right shows the container upon the introduction of different gas types, gas A, B, and C. Based on the theory, gas molecules are too small in comparison to the container. It can be referred then the size and identity of the gas does not matter. This means introduction of B and C in a container can be thought as of adding more amounts of A. If more molecules are introduced in the container, more frequent collisions are expected. Eventually, more pressure is exerted. The total frequency of the collision with the container walls is then the sum of the frequencies of collision made by each gas type, as thought it is the only component present. Since the frequency of collision is related to the pressure exerted by the gas, the total pressure is equal to the sum of the partial pressures of the different gas types. Hence, the formula for the pressure total is equal to P of A plus P of B plus P of C. It is important to take note that not all conditions do gases behave ideally. This means that not all gases at certain conditions can be governed by the ideal gas equation or any gas laws. Such gases are referred to as real gases. To allow real gases to behave somewhat like an ideal gas, the gas particles must be far away from each other, and the particles must possess kinetic energy so high that it can overcome the potential energy in the form of attractive forces between molecules. To meet those requirements, gases must be at the idealizing conditions. The idealizing conditions are at high temperature and low pressures. At high temperatures, the partial pressures or the particles possesses kinetic energy so high that it can overcome the potential energy in the form of attractive forces between molecules. At low pressures, the gas particles are far away from each other. To meet those requirements, gases must be at the idealizing conditions. The idealizing conditions are at high temperature and low pressure. At high temperature, particles possesses kinetic energy so high it can overcome the potential energy in the form of attractive forces between molecules. At low pressures, the gas particles are very far apart from each other. And it can be okay. It can be expressed in the kinetic energy and speed of electrons are related to one another according to this equation, where Ke is equal to 1/2 times mv raised to the power of 2 with a subscript of RMS, where Ke is the kinetic energy and m is the mass, and v with the sub of RMS is the root mean square speed. Although average kinetic energy is constant at fixed temperature, not all gas particles move at a constant speed. The Maxwell distribution of speeds is a function showing the fraction of particles of a certain gas that possesses a certain speed at a given temperature. For a particle with molar mass, the fraction of particles f of v possessing the speed of v at temperature is given by f of v is equal to 4 pi multiplied with m over 2 pi RT raised to the power of 3 over 2 multiplied by v raised to the power of 2 multiplied to e raised to the power of negative mv2 over 2 RT. The plot for this function is shown on the right. Varying temperature and molar masses, we can see that the most particles at high temperatures and lower molar masses tend to have greater speeds, while most particles at lower temperatures and higher molar masses have lower speeds. There are three important speed values that can be found in a Maxwell distribution of speeds. The first one is the most probable speed. The most probable speed, or VMP, is the speed that is most likely possessed by the largest fraction of molecules. The most probable speed is equal to the square root of 2 RT divided by m. The mean speed, or V bar, is the average speed for all particles. The mean speed is equal to the square root of 8 RT divided by the quantity of pi times m. The root mean square speed, or the VRMS, is the speed of the particles possessing the average kinetic energy. The RMS speed, or square root of 3 RT divided by the m. To summarize, incorporation of ideal gas equation in dealing with stoichiometric calculations involving gaseous reactants or products is important in order to convert the amount in moles of substance to its volume or vice versa. Here are our references or bibliography. Thank you and God bless.